Hi there. Today I wanted to make a video talking about some of the important terminology and ideas around chemical reactions and how they relate to energy in biology. So we'll spend the next few minutes talking about that and see if it can help clarify some of these points. So the first thing we're going to have to do when we talk about chemical reactions is we're going to represent those chemical reactions visually. So in biology, we always represent chemical reactions with an arrow. This arrow is going to represent the chemical reaction happening. It's going to cause some changes to some other molecules. On one side of the arrow, here on the left, we're going to put the things that go into this reaction. So in this case, I'm indicating a couple molecules. These molecules are glucose and oxygen. Okay, so glucose and oxygen are going to go into our chemical reaction, this arrow. And then on the other end of the arrow, we're going to get out some things that our chemical reaction produces. So in this specific example, we're going to get out three things. We're going to get out carbon dioxide, we're going to get out water, and we're going to get out some energy. And so this is a chemical reaction, right, that begins with glucose and oxygen. The chemical reaction happens, and we get out carbon dioxide, water, and energy. We're going to talk a lot about this specific chemical reaction in this course. This is what we call cellular respiration. This is how we get the energy we need to operate our cells in our bodies. Okay. So there's a couple important terms I want you to know anytime you look at one of these chemical reactions. And the first is that we have specific names for the things that go into a chemical reaction. So the things before our arrow we call either the reactants or the substrates. So those two words mean the same thing. Reactants or substrates are the stuff that goes into our chemical reaction. And then on the other side of the arrow, we're going to show the products of the reaction. So whatever our chemical reaction produces, what we get out of the reaction are what we call the products. So beyond that, we're going to add some additional terminology to our discussion of chemical reactions. So I've created a list of the vocabulary I want to make sure we understand before we move on and start to talk about specific chemical reactions and how they work. So the list includes reactants or substrates, what we just talked about. Again, the products, what comes out of our chemical reaction. And then we're going to add 5 more terms and think about what they mean. So we're going to discuss what it means for a chemical reaction to be exergonic. We'll then discuss what it means for a chemical reaction to be endergonic. We'll think about anabolic chemical reactions. Then we'll discuss catabolic chemical reactions. And finally, we'll end our discussion with about a molecule called ATP, or adenosine triphosphate. And this molecule is particularly important for chemical reactions involving energy. Okay, so let's begin by talking about an exergonic chemical reaction. So this term exergonic refers to chemical reactions that release energy. So this graph indicates what an exergonic chemical reaction looks like over time. And so here our graph begins with some reactants. Okay, and their placement on this graph indicates how much energy they have. So they're a little bit up the axis here. That means they have some energy in them. As we proceed from left to right, that's going to indicate what's going on during our chemical reaction. And so as we go from left to right, we get to our products, what we get out of our chemical reaction. And you can see that the products are much lower on the axis for energy. So during our chemical reaction, we began with reactants that had energy in them, and we ended with products that have less energy in them. So our chemical reaction released energy out of the reactants. So that is an exergonic chemical reaction. Any chemical reaction that releases energy out is exergonic. So you might infer that endergonic reactions are going to be the opposite. An endergonic chemical reaction is going to require some energy. So let's look at the graph for this reaction. Again, here are the reactants that we will begin with. They have a certain amount of energy in them. As we proceed from left to right, we're going to proceed through the chemical reaction, and we end up with these products. The products now have a higher amount of energy than the reactants began with. For that to be true, it means that we had to put some energy into this chemical reaction, and that energy is now stored in these products. Okay, so an endergonic chemical reaction requires the input of some energy. Okay, so exergonic releases energy, endergonic requires energy be put in. So how about the next term? The next term is an anabolic chemical reaction. And the best way I can describe an anabolic chemical reaction is to say that they are building reactions. So let's think of a really simple example. Let's imagine some Legos. So we've got a pile of Legos here, and we're going to do a chemical reaction on these Legos. Our chemical reaction is going to result in a built-up structure. So we've made this house. We've taken these individual pieces, and in our chemical reaction, we put them together into something larger and more complicated. We built something. That is an anabolic chemical reaction. Let's think of an example that's more directly related to biology. So when we talk about photosynthesis, we'll be thinking about this exact chemical reaction. We're going to take 6 of these carbons, 6 CO2s, and 6 waters. We're going to do a chemical reaction. We're going to put them together into one glucose molecule and some oxygen. So we're taking 6 of these carbon dioxides and we're putting them together into one glucose molecule. We're taking several small pieces and putting them together into one larger molecule. So anabolic chemical reactions are chemical reactions that take smaller pieces and put them together into larger molecules. The thing about these kinds of chemical reactions is that anabolic chemical reactions require energy. So all anabolic chemical reactions are endergonic. They always require energy be put in to make them happen. So I always had trouble remembering the different, or what it meant for a reaction to be anabolic. And at some point I realized, I was thinking back on my childhood, and I was remembering, and during my childhood, that baseball players started to take anabolic steroids so that they could grow larger muscles and hit more home runs. So I always think back to that. I go, anabolic reminds me of anabolic steroids. Anabolic steroids help build larger muscles. So anabolic reactions are building reactions. We build larger things when we do that. That's how I remember, and I hope that'll help you. So what about catabolic reactions? Catabolic reactions are going to be breakdown reactions. So they're basically the opposite. So again, we can imagine our Lego house here. If we do a chemical reaction where we take that apart into its individual pieces, we just broke down the house, that is a catabolic reaction. Again, this happens in biology, and we'll be talking a lot about catabolic reactions. One of those catabolic reactions is cellular respiration. Cellular respiration takes this first molecule, glucose, combines it with oxygen that we breathe in. We do a chemical reaction, and we get out 6 carbon dioxides and 6 waters. We break apart the glucose into smaller molecules, carbon dioxide. So the thing to remember about catabolic reactions is that they break larger things down into smaller pieces. And then catabolic reactions release energy. So anytime we take these larger things apart into smaller pieces, we get energy out. That makes catabolic reactions exergonic. Okay, so anabolic reactions are endergonic, and catabolic reactions are exergonic. Right, so if we understand those 4 terms, we should be able to accurately discuss any chemical reaction. So the next piece that we want to put together for understanding chemical reactions and energy is the role of this molecule called ATP. ATP is the energy currency in our cells. So we're going to think about what that means. We'll start with a simple example. I think of ATP like a battery. ATP is like a charged up battery. When I have a charged up battery, I can put it into something and use it to do some work. And that's what we can do with ATP. But once I've used my battery, I end up with a dead battery. The same thing is going to happen to ATP. The dead battery form of ATP is called ADP. Okay, so we've got a charged up form. The energy storing unit is ATP. And if we use the energy up, we get ADP back, right? So again, anytime we need to do something in the cell that requires some energy, we're going to use ATP. So we're going to take ATP, we're going to use that energy out of ATP to power anabolic reactions. So anytime we're going to do an anabolic reaction in the cell where we're going to put something together, it's going to require some energy. We're going to get the energy out of ATP. But now we've got this dead battery. And much like with rechargeable batteries, we don't want to just throw this away. We can reuse it. We just have to recharge it. So in cells, we can recharge this dead battery by putting some energy in, and we'll reform ATP. The energy that we put in comes from catabolic reactions. Remember that catabolic reactions, breakdown reactions, always release energy, and we can put that energy into ATP. Now we've got a recharged battery. We can use it to power another chemical reaction, an anabolic chemical reaction somewhere in the cell. We'll get our dead battery back out, but that's fine. We'll just recharge it somewhere else in the cell where a catabolic reaction is going on. And now we've got our recharged battery. So that's the role of ATP. It helps power reactions, and it captures the energy that comes out of catabolic reactions. So here's a more detailed diagram of ATP in this relationship. So at the top, we've got ATP. Again, we'll take energy out of ATP to power a chemical reaction, and we'll get ADP. That's our dead battery form. And then we'll put energy back into ATP, into ADP to get ATP out. That's our recharged battery. I just wanted to show you the chemical structure. I would never ask you to draw the chemical structure, but I wanted to point out how ATP can store energy. And it's all about these 3 phosphate units on the left side of the molecule. These 3 phosphate units, each of them has a negative charge on it. We know that like charges repel one another. So these 3 phosphate groups with their negative charges on them are pushing apart on one another, but they're held together by chemical bonds. So if we break one of these chemical bonds, this phosphate group will go running away as fast as possible because it's repelled from the other negative charges. So breaking the bond causes this phosphate to move away rapidly, and that's kinetic energy. That's where the energy comes from in this molecule. So when we break this off, we release a phosphate group, and we end up with ADP. Here, the D stands for di. So it's adenosine diphosphate. There's just 2 phosphate groups. When we take energy from a catabolic reaction, we can use that energy to force another phosphate back onto the end. Now we've got 3 phosphates again. That's adenosine triphosphate. So the ATP stands for adenosine triphosphate. ADP stands for adenosine diphosphate. Again, triphosphate is the charged up battery. Diphosphate is the dead battery. And we're going to use this ATP molecule in all of the energenic chemical reactions that we're going to talk about, like cellular respiration and photosynthesis. So as always, I hope that helps. If you have any questions, I'll look forward to answering them on the discussion board, and I will talk to you soon.